Hello everyone, and welcome back to this journey through complex analysis. Today we're going to be continuing our exploration of complex variables and complex functions and the set of complex numbers, and start to build some of the more important functions that are associated to complex variables in the set of complex numbers, in particular the complex exponential and the complex logarithm. So what did we talk about last time? Well, the last time we talked about the set of complex numbers, what it is defined to be, and what stands it out, say, compared to the set of real numbers. In particular, the set of complex numbers is just a bunch of objects which can be viewed as a linear combination of real numbers, x and y, with the variable that differentiates them is this new object that we have to define, the square root of -1. Under this particular definition, we then have to define addition, subtraction, multiplication, and division on this set of numbers, which we definitely did. We also discussed and also proved that C, the set of complex numbers, is not orderable. So for example, if you pick any z1 and z2 in this set of complex numbers, this statement doesn't necessarily make sense unless you're looking at, for example, a particular subset, say the reals, which is a subset of the complex numbers. But this doesn't make sense, and you cannot define such a symbol statement that will make sense on the set of complex numbers as it did in the set of reals. We also discussed this e to the I theta is equal to cosine theta plus I sine theta statement, which is sometimes called the Euler-Cotes identity, which kind of connects the exponential function to cosine and sine. So we're like, okay, well, if e to the I theta is equal to cosine theta plus I sine theta, maybe we can view the exponential function as a periodic function, maybe. But this particular statement doesn't really make sense in the complex sense because we haven't defined it, which is one of the things we're going to do today. And similarly, what does it mean to exponentiate complex numbers to a particular power? We haven't defined that either, right? But if such a thing does make sense, then it's going to be equal to almost like a shift in the phases of cosine and sine. And sometimes people refer to this as the de Moivre identity. So the de Moivre identity. So we have the Euler-Cotes identity, which connects exponential functions with trigonometric functions, and we also have de Moivre's identity, which is going to connect complex numbers to just phase shifts of their particular angles. So what I want to do today is in particular define for you what a complex exponential even means, and also discuss its quote-unquote inverse function, the logarithm, and sort of see how that operates in the set of complex numbers as well. And then eventually we're going to discuss what it means to do a power of a complex number and what that actually means from an algebraic and also a geometric sense at a later time. So keep in mind, for any z in the set of complex numbers, we can represent z in at least one of two ways. The first is of the form x plus iy, and the second is r e to the I theta. And just for some terminology, this x plus iy is sometimes referred to as the rectangular form of the complex number. So that's the rectangular form, like a rectangle. So a rectangular form of a complex number, and this REI theta is sometimes referred to as the polar form or the trigonometric form of the complex number as well. And if you do not know what R and theta are, then R, sometimes called the magnitude of the complex number, so sometimes you'll see it written as the norm of z. This is just going to be equal to the square root of x squared plus y squared. And some people will also use that as absolute value, so try and make sure that the notation that you're using is consistent. And then theta is defined to be equal to the argument of z. And keep in mind, this argument of z, as we did last time, this is definable in terms of the arctangent function, right? It's not as easy as one might think, it's arctangent y over x. There is a little bit more of a definition that you have to be more precise with that particular argument. Right? So now let's talk about this statement, e to the I theta. Right? So now we need to answer the really big question of today. What does e to the I theta even mean? because up to this point we only have that e to the x is defined for the set of real numbers. But what is e to the I theta, where I is a complex number and theta is a real number? So let's start off with our very first definition. So e to the z obviously is going to be a function from the set of complex numbers, and let's take the codomain to be equal to c, and let's assume that z is equal to x plus iy, where x and y are real numbers. Then we're going to define e to the z to be equal to the following. We're going to define it to be e to the x, so that's a real number, times cosine of y plus I sine of y. And why is this definition sufficient? Well, first off, that's a real number because e to the x maps r to r. That's a real number. That's a real number. This here is a complex number. R is a subset of c, so we have a complex number z1, a complex number z2, and the product of them, and we already know that that's going to be defined to be a complex number as well. So here we have the set of the e to the z function is now well defined from c to c. Now, why in the world would we want to define e to the z like this? Well, if we define it to be this, then what is the resulting statement? So e to the z then will be equal to e to the x times cosine of y plus I sine of y. But you might remember that this, from the Euler-Cotes identity, is just going to be equal to e to the x times e to the iy, because y is just taking the place of theta. So what is one of the properties that we would like exponential functions to have? Well, keep in mind e to the z is the same as writing e to the x plus iy. So we're going to define this function as this because in some sense we would like this decomposition to follow. Because remember, in the set of real numbers we have that e to the a times e to the b is equal to e to the a plus b. So we would like that identity to kind of be preserved under this complex definition. So if we define e to the z to be equal to this particular complex number, which is well defined, then we have that e to the x times e to the y will be equal to e to the x plus iy, and that will come as a corollary to this particular definition, right? So everything in terms of that decomposition of exponentials property is well preserved in this definition. So that's one of the reasons why we actually define e to the z this way. Now, obviously, we get several other corollaries as a result. So, for example, we don't have to do e to the x or e to the iy and multiply them together to get something like this. Technically speaking, you can do e to the z1 times e to the z2, and you're going to get e to the z1 plus z2, and that's going to be true for any complex numbers z1 and z2 under this particular definition. And you're also going to get a similar theorem for the quotient of two complex exponentials, which will result in e to the z1 minus z2, which will follow parallel, of course, to the real number exponential function. Before moving forward, since we've now defined the complex exponential, each of these statements here, e to the iz and e to the minus iz, are all going to be well defined, and pretty much these statements will be defined as well, since they are complex numbers as a result. And from that, we can then define four new functions, sine, cosine, hyperbolic sine, and hyperbolic cosine, to all be equal to these particular statements. So under these particular definitions, and if you've never seen these statements before, you might be thinking, oh, they actually look kind of strange. But I leave to you to verify that they will have the same exact similar properties to that of their real variable counterparts. For example, sine squared z plus cosine squared z will be equal to 1. And that's a fun little exercise to show that is going to be true for all z in the set of complex numbers, just like it did for the reals. And similarly speaking, cosine squared of z hyperbolic minus sine squared hyperbolic of z will also be equal to 1 as well, just like it did in the real case, right? But those are just some algebraic exercises that you might want to try on your own, but these are going to be well defined since we've already defined our complex exponential e to the z. Now, I want to bring up one very important property of the exponential. So one very big difference between e to the x and e to the z. So take a guess. What is the biggest difference, right? Because we have this decomposition of e to the z into a product of e to the x and cosine y plus I sine of y. But the biggest difference is that e to the z is periodic. E to the z is a periodic function, just like sine and cosine. So if it is just like sine or cosine, then what is the period of this function, f of z is equal to e to the z? So you might be thinking, well, it has sine and cosine in it, so is the period going to be equal to 2 pi? Actually, no. Right? So let's see if we can build what the period is for this periodic function e to the z. So what do we mean by periodic? So that means that e to the z plus p is going to be equal to e to the z for all z in the set of complex numbers. So our goal is to find out what is this period p going to be equal to. So by properties of the exponential, what do we know about e to the z plus p? Well, that's just going to be the same as e to the z times e to the p, and that's going to be equal to e to the z, right? And we've already proven that that is the case. So the next statement that I want to say is, okay, can I divide both sides of this expression by e to the z? Question mark. Well, you should be able to think about this. Maybe I can, maybe I can't. But one property that you definitely need to verify on your own is that e to the z is not going to be equal to 0 for any z in the set of complex numbers. So this is going to allow you to do this particular thing, right? So they're going to cancel out. And then we're just going to be left with what? So then we're going to be left with e to the p is equal to 1. So what is p? Well, p is going to be some complex number, let's assume, a plus bi, where a and b are going to be real numbers. Now, a could be 0, b could be 0, and we're just trying to figure out, what is the possible values that a and b can have for this statement. So let's just see what that actually is going to be equal to. So if I take the norm of it, because if e to the p is equal to 1, that means e to the p must be equal to the norm of 1 as well. And the absolute value of 1 is just going to be equal to 1, so that's not going to be very exciting as well. So we're just going to have e to the a plus bi. It's just going to be equal to 1, meaning that the norm of e to the a times e to the bi will also be equal to 1 as well. And another property for complex numbers that you should be able to verify is that the absolute value of z1 times z2 will be equal to the absolute value of z1 times the absolute value of z2. And this is going to be very, very important. And here is the first case. So once we decompose this absolute value, we're going to have the absolute value of e to the a times the e to the bi, and its absolute value must be equal to 1. Now, firstly, what is the absolute value of e to the bi? Well, the absolute value of e to the bi will be equal to the absolute value of the number cosine of theta plus I sine of theta, which, keep in mind, this is the real part, this is the imaginary part. So this is going to be equal to the square root of the real part squared plus the imaginary part squared. But sine squared theta plus cosine squared theta is going to be equal to 1. Keep in mind, theta is going to be a real number. So that's going to be equal to the square root of 1, which we know to be equal to 1. So that means this part just vanishes into 1, and then we're just going to be left with the absolute value of e to the a will be equal to 1. Right? So now we have at least a basic statement of what the solution is. Right? Now, before moving forward, I just want to make a very important statement, in particular, for a complex number z. What do we actually get from this particular decomposition? E to the x dictates the magnitude of z. And well, why is that the case? Well, if z is equal to a plus bi, then we have e to the a and e to the bi, but the norm of e to the bi is always going to be equal to 1, and we're always going to be left with this e to the x term. And that's going to dictate the norm of that particular number, right? So that's the first thing that we need to notice. And then, well, what about this e to the y term? So the e to the iy term actually is going to dictate the direction of z. Because keep in mind, from the geometric perspective of complex numbers, we have the norm of the particular complex number, and we also have the direction, which can be represented in terms of its argument. So we have e to the x dictating its magnitude, and e to the iy dictating the direction of that particular number z. Because keep in mind, what we're actually trying to find here is we're trying to find the period of the exponential function, right? So we're trying to solve the equation e to the p is equal to 1, and we say, okay, that's the same as if p is equal to a plus bi, the same as the norm of e to the a is going to be equal to 1 as well. So now we're just trying to solve this particular equation for a, right? And then we can find b as a corollary if we want. So what does that mean? So if e to the a times e to the bi is equal to 1, and the norm of both sides of this equation is going to be equal to 1, that means the norm of p will be equal to 1 as well. Right? Does that make sense? So if e to the p, or not necessarily p, but the norm of e to the p will also be equal to 1 as well, because e to the p is going to be a complex number, and we're trying to find the value of p. So if the norm of e to the p is equal to 1, where is e to the p located? Well, e to the p is just going to be located on some particular point on the unit circle, right? So e to the p is located here, 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 or here, right? So e to the p could be equal to 1, it could be equal to -1, it could be equal to I, it could be equal to -I, and so on. Okay, so that is going to be giving us this. So now that we know the norm, which is dictated by e to the a, now we just need to find what b is going to be equal to. So we have that e to the a times e to the bi must be equal to 1. So we clearly see from this equation that a must be equal to 0, because that's the only way that this equality is going to be generated. So if a is going to be equal to the 0, that means e to the bi must be equal to 1 as well. Right, that's the only way that's going to match as well. Because when a is equal to 0, e to the 0 is going to be equal to 1, and then we're going to have 1 times e to the bi is going to be equal to 1. And keep in mind, why is that? Because this is dictating the norm, and the norm of this number is equal to 1. Right? Because this is always equal to 1, and 1 times something must be 1, so that means that number must be 1 as well, forcing a to be equal to 0. So now that we have this new equation, e to the bi will be equal to 1, and let's just re-outline what we're looking for here. So we're saying e to the z plus p will be equal to e to the z for all z, and we're like, okay, if that's going to be equal to the case, then that means e to the p must be equal to 1, which means e to the a times e to the bi must be equal to 1, and we already know that the norm of that part is always going to be equal to 1, so e to the a times e to the bi must be equal to 1, forces a to be equal to 0, and now we're just trying to figure out, okay, what is b equal to now? So from this equality, what do we get? So e to the bi by the Euler cosine identity is going to be the same as the cosine of b plus I times the sine of b, and this must be equal to 1 as well. And keep in mind, this is a real number. This is a real number. So if this is a real number, that means this must also be a real number as well. And if this is a real number, that means this term must be equal to 0, which means that the sine of b must be equal to 0 as well. And cosine of b must equal to 1, right? So sine of b must be equal to 0, and the cosine of b must be equal to 1. So what value of b in the set of reals will make this true? Well, from basic pre-calculus, you should know that b must be equal to 2k pi. Now that we have what b is, and we also know what a is, because keep in mind, a was equal to 0, now we know what p is. So that means p, keep in mind, was decomposed into a plus bi. A was equal to 0, and now b is going to be equal to 2k pi, and don't forget that little I. Now we just have 2k pi I. Right? So that is the period of the exponential function. Right? So let's just formally state that here. So that means the period of f of z equals e to the z is 2k pi I, which is very different than just 2 pi, right? So what do we say as a result of that? That means e to the z plus 2k pi I will be equal to e to the z for all z in the set of complex numbers, right? So now we have that e to the z is indeed a periodic function in the realm of the complex numbers with period 2k pi I. What do we get as results from that? So since e to the z is periodic in the set of complex numbers, e to the z is not going to be one-to-one in C neither. So let's just keep in mind what we mean by one-to-one. So if we look at the set of real numbers, for example, sine or cosine, and we draw a line, for example, at y is equal to 0.5, it does not pass the horizontal line test. So if we try to invert this by switching x and y, it's not going to pass the vertical line test either. So since e to the z is not periodic, that means a generalized inverse of e to the z will not be a univariate function. It will not be a univariate function because it's not going to pass the vertical line test either, which means we have to restrict our domain if we want to build a univariate function, which we're not going to, but you definitely can. So what do we want to do now? So now we want to define, so what was the inverse of exponentials in the real world? Well, that was obviously going to be the natural log function. So we want to define this function such that what is true? So what type of properties do we want the log function to have? Well, if e to the omega will be equal to z, then we would like that the natural log of z to be equal to omega. But keep in mind, exponentials are periodic functions. Therefore, this is going to be the same as omega plus p, right? And this is the case since e to the z is periodic. Right? So since e to the z is periodic, right? So if e to the omega is equal to z, then the natural log of z will be equal to omega, or any phase shift thereof of it with multiples of 2 pi I. Right? So now that we want this property established for this function natural log of z, which we currently do not know, let's see if we can define it with some other properties. So let's assume that z is equal to x plus iy, and let's also assume that it has polar representation r e to the I theta, r its magnitude, theta its argument, and also let's assume that omega is equal to u plus iv. So what do we want? So we have that z is equal to e to the omega by definition. So z is equal to e to the omega, and keep in mind what is z. So that means that z, which is x plus iy, will also be equal to e to the u plus iv by definition of z and omega. So if we look at x plus iy in polar form, then you're going to have r e to the I theta will be equal to, and exponential functions can be decomposed across their sum arguments as u e to the u times e to the iv. From here, I can take the norm of both sides of this expression, so the norm of r e I theta will be equal to the norm of e u times e to the iv. And now we can use the properties of exponentials because this is going to be equal to what? So it's the norm of r times the norm of e to the I theta is equal to the norm of eu times the norm of e to the iv. Keep in mind, complex numbers magnitude is dictated only by its leading term because this is going to be equal to 1 and that's going to be equal to 1. So we're just going to be left with the absolute value of r will be equal to the absolute value of e to the u. Once we have this, then we can clearly see that r will be equal to e to the u. And then therefore, what will this be equal to? So that means, keep in mind, this is a real number. This is a real number too. Therefore, this is just an equation in the real domain. So therefore, we can use the properties of natural logs and be like, okay, if r is equal to e to the u, that means u must be equal to the natural log of r. Right? And keep in mind, what is r? R is just the net absolute value of z. So that's what u is going to be equal to. So now that we know what u is for our particular statement, because we're trying to say, okay, if e to the omega is equal to z, then this is going to be the natural log of z is equal to omega plus p. We're trying to figure out what omega is going to be equal to, because we already know what p is going to be equal to, and now we're just trying to figure out what is omega, because omega is represented as u plus iv. Now we know what u is, now we need to figure out what v is, where v is the argument of that particular number. So looking at the other piece of this equation, we have that e to the I theta must be equal to e to the iv, because those exponential terms must be equal, since now their magnitudes are going to be equal. So if e to the I theta is equal to e to the iv, that means that v must be equal to theta, where theta is equal to the argument of z. So now we know u, now we know v. So now we have reasonable forms to define our natural logarithm. So let's go ahead and do that. So the natural log of z will be defined as follows. We're going to define it to be equal to u plus iv plus p, where u is defined to be equal to the natural log of the norm of z. So the natural log of the norm of z, and then plus I times the argument of z plus 2k pi I. Now notice that I have the natural log on the left and the natural log on the right. I'm going to denote the one on the right hand side by a subscript of 0, where this is your typical real valued logarithm. Right? And keep in mind the norm of z is always greater than or equal to 0. Right? So this is only going to be true provided that z is not equal to 0, right? So the natural log of 0 will not be defined in the complex plane, just as it was not defined in the real plane, right? So now we have the natural log of z, where z is a complex number, is defined to be equal to the natural log of its argument in the real number sense, plus I times its argument plus 2k pi I, where that 2k pi I is known as the period of the associated exponential function. Now let's go through a couple examples just to make sure you know how to use this definition of this logarithm. So we have our exponential function defined in C, and now we have our natural log defined in C. So now let's calculate just a couple of basic things. So what is the natural log of e in the complex sense? Well, we already know that's going to be equal to 1. Also, every time you see this natural log subscript 0, some people usually call this the principal branch of LM, right? Because there's actually many branches of natural log because it's a multivariable function. So 0 is kind of the normal one that you probably are already used to from the real number world. So the natural log principal branch of e will be equal to 1, but what is the natural log of e in the complex sense? Well, what do we know? Well, we already know that the norm of e is going to be equal to e because e is a real number, and also the argument of e will be equal to 0 because where is e? Well, e is approximately 2.71828, so with respect to the complex plane, where this is the real part of z and the imaginary part of z, the argument of this number is located right here because that is e, so the argument of z is 0, the norm of e is e. So by definition of the natural log in the complex sense, we have that the natural log of e will be equal to the principal branch natural log of e plus I times its argument, 0 plus 2k pi. Notice I factor out my I here. But this is just going to simplify to what? So the natural log principal branch of e is going to be equal to 1 and then 2k pi I. So that's what the natural log of e is equal to. So actually in the complex sense, the natural log of e is not just equal to 1, it's actually equal to infinitely many things, right? But if we take the principal branch of e, where the 0 now corresponds to what k is, then we're going to have that's just going to be 1 plus 2 times 0 pi I, which is going to be equal to our familiar value of 1. So this is called our principal value of the natural log of e. Okay, but you can of course take other branches of e. For example, if I say what is the second branch of the natural log of e, well that's just going to be equal to 1 plus 2 times 2 pi I, which is going to be 1 plus 4 pi I, which obviously is a number that's not real but completely complex. Now let's look at just another one, just to make sure we understand. What is the natural log of minus 1? Well, in the real numbers, this is not defined because the natural log is defined on the positive reals, but in the complex number, maybe this is going to exist. So where is minus 1 going to be located? Well, minus 1 is going to be located all the way over here, so its argument, theta, is going to be equal to pi, and its norm of minus 1 is just going to be equal to 1. So by definition, this is going to be equal to the principal branch value of its norm plus I times its argument plus 2k pi. And then once we have this, well, we already know that the principal branch value of the natural log of 1, that's just going to be equal to 0. So we have 0 plus I pi plus 2k pi I. And then we have that that is going to be the natural log of minus 1. So I can ask you, okay, well, if that's the answer of the natural log of 1, what is the principal branch value of the natural log of minus 1? So the natural log principal branch of minus 1 will be equal to I pi plus 2 times 0 pi I, and then we see that that's just going to be equal to I pi. Right? So it's very important to notice that the principal branches are not necessarily real numbers, as we clearly see here, right? So the principal branch value of the natural log of minus 1 in the complex plane is I pi, but in the sense of the real numbers, the principal branch of the natural log of minus 1 is undefined, right? Because this has no real part, and hence it's undefined in the set of reals. Obviously, there's several other properties associated to the logarithms, and I'll give you one here that you can show, but the natural log of z1 times z2 will be equal to the natural log of z1 plus the natural log of z2 for all complex numbers, z1 and z2, as long as they're not equal to 0. But you also get the natural log of the quotient of the z1, z2s also, and you're going to get the minus counterpart, as was seen in the set of reals. So this is how you define the complex exponential and the complex logarithm in the realm of the complex numbers. And what have we figured out? Well, we figured out the exponential function is periodic with period 2k pi I. And also the complex logarithm is a multivalued function, and hence it has multiple branches. And if you want a particular value, you can always pick a particular branch to get its value, provided that it is defined. And the natural log of z is defined for all z not equal to 0. But exponential functions and logarithmic functions are not the only functions that are important in the world of mathematics. So in the upcoming videos, we're going to be learning more about other functions that you probably have learned in the set of reals, and also discuss how they behave in the realm of the complex plane. I hope to see you there, and I hope you enjoyed this video. Take care.